He's even worse when he's locked back there.
He likes to sing. He's vocalizing.
Mother, shh. Good morning.
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 First, are there any questions or concerns? You guys feeling as awake as I am right now?
Absolutely.
Okay, all right, we're in the same boat. Good. I think I did get Catherine or Kate, Roberto, you did send me a message. I didn't get a chance to really look at it. But I will look at it later today. Other questions? So I want to finish the majority of the nervous system today. Wait just for a second here. Oh, what am I doing? Sorry, give me one moment. Sure. So we were talking about the myelin sheath the last time. That's where we ended. And the Schwann cells do the myelin, put down the myelin sheath in the peripheral nervous system. The oligodendrocytes do it in the central nervous system. Remember that they're a little different in the way they do it. The one when the Schwann cells are putting down the myelin sheath, they put down the myelin sheath one cell, one segment. One Schwann cell, one segment. Oligodendrocytes put out multiple extensions, and each extension wraps around one segment of one axon. Can they myelinate multiple sections on one axon? Yes, but they can also do up to 15 different sections on different axons. However, because they're just doing segments, each there's going to be gaps that aren't covered by myelin. These gaps are called the nodes of Ranvier, named after probably the person who discovered them. Also, right before the first segment of myelin, and right in between the soma and the first segment of myelin, is what we call the axon hillock. And in this segment, before the first segment of myelin, is what we call the trigger zone. It's an important role. It has a very important role in initiating a nerve signal. Little segment right here. Just for medical interest, we were talking about the myelin. Multiple sclerosis is an autoimmune disorder. If autoimmune meaning the body is attacking itself, it's where the body has essentially decided that some part of the body is foreign and needs to be attacked. It's a pretty common. There's a lot of autoimmune disorders out there. Type 1 diabetes is probably the most common and most well known, where it's an autoimmune against the insulin secreting cells. But multiple sclerosis is an autoimmune disorder that is where the oligodendrocytes and the myelin of the central nervous system are under attack. So as a result, the myelin and the oligodendrocytes of the central nervous system deteriorate. And as they are destroyed, they're replaced by hardened scar tissue. Remember what glial cells of the central nervous system put down scar tissue? Do you remember? No, it's been a whole week. So we have 4 different types of glial cells in the central nervous system. The oligodendrocytes, the microglial cells, they're part of the immune system. Now my head is kind of foggy all of a sudden. Microglia, oligodendrocytes,
Astrocytes.
astrocytes, and what else? Ependymal cells. So astrocytes are the ones who are putting down the scar tissue here. This, if you think about it, the myelin is like the rubber insulation around electrical systems in your house. What happens when that gets broken down? You lose charge in that wire. There's less conduction of that wire. So what ultimately is occurring here is there's a disruption of nerve conduction. A few will die within 1 year of being diagnosed, but others will live 20 to 30 years. Each neuron in our body has a lifespan of how long? Someone tell me. Do they undergo mitosis? How often do you see tumors that are forming from the neurons? Most tumors are forming from the glial cells. So how often do we see regeneration of neurons? Or redivision and mitosis of neurons? We don't. So the average neuron has an average human lifespan. A little bit more about this. We have myelinated nerve fibers and we have unmyelinated nerve fibers. Many nerve fibers in the central nervous system and peripheral nervous system are unmyelinated. Well, what's the overall structure for these unmyelinated nerve axons? If you think nerve fibers are axons. So unmyelinated nerve fibers how are they arranged? They're enveloped in the Schwann cells that myelinate other nerve fibers. If you remember, one Schwann cell can wrap around one segment of the axon around 100 times, up to 100 times. In the last fold of the Schwann cell around the axon is the neural lemma. In the outer folds of the neural lemma are where these unmyelinated nerve fibers are found. So this neural lemma membrane wraps around these unmyelinated nerve fibers one time. So remember, in myelinated, the Schwann cells can wrap around them up to 100 times. In the unmyelinated nerve fibers, they're wrapping around them once. Some terminology to keep in mind and cement this into your brain. It'll make your life easier and my life easier over the next couple of weeks if we keep these terms in mind. Neuronal cell bodies. A ganglion is a cluster of neuronal cell bodies in the peripheral nervous system. A nucleus is a cluster of neuronal cell bodies in the central nervous system. So ganglion in the peripheral nervous system, nucleus in the central nervous system. In axons, a bundle of axons in the peripheral nervous system is a nerve. A bundle of axons in the central nervous system is a tract. Nerve tissue is also grouped into two basic regions, gray matter and white matter. White matter are aggregations of myelinated axons. The lipid part of the myelin is what gives it the white appearance. The gray matter is formed from neuronal cell bodies, dendrites, and unmyelinated axons and neuroglia, and it lacks myelin. So everything, let's do it this way. Let's organize it correctly this way. Only the myelinated axons are considered part of white matter. Everything else is gray matter. When we're thinking about the central nervous system, all white matter is myelinated axons. Everything else is gray matter. The white is is the appearance of the lipid, which we know is the majority of what myelin is. Nerves are found in the what? Well, tracks are found in the what?
Nerves. Nerves are found. A.
That's right. So nerves are found in the peripheral nervous system, while tracks are found in the central nervous system. Remember, nerves and tracks are bundles of myelinated axons. Do you guys want to see what my teaching assistant is doing while we're having class?
Snoring. I can hear him.
Can you hear her? That's
Yeah.
terrible. Oh,
How old is he?
she is actually, she's about she'll be 11 in a little while here on Halloween. I didn't realize that you could hear her. That's funny.
It's just, yeah, better than the one snoring next to me.
So nerve conduction in the axons depends on two factors: the diameter of the fiber. The more surface area the fiber has, the faster the conduction is. And whether there's myelin or not. In small unmyelinated fibers, the nerve signals travel at about 0.2 to 0.5 meters per second. In myelinated fibers of the same small size, nerve fibers travel up to 3 to 15 meters per second. In large myelinated fibers, nerve signals can travel up to 120 meters per second. So size and presence and absence of myelin. So question, why are not all nerve fibers myelinated? I mean, we like things to be fast, right? It's the reason fast food restaurants make a lot of money, is we like things to be fast. Well, do we want all nerve conduction to be fast?
No.
Sometimes you want certain things not to happen immediately and maybe take a little slower response time, and other things to be a lot faster. If you grab the wrong end of the curling iron in the morning, you hopefully that will be a fast nerve conduction and you'll drop it. Had a student the other day say that she actually watched her hands sit there and blister as she was holding the curling iron. It's a little scary. But most of us don't have that happen. It happens really, really fast. So we like some to be a little slower than others. One thing you'll notice is that when you, if and when you ever grab the wrong end of the curling iron, you drop it and then you sense the pain. Because you want your pain conduction is much slower. Your pain nerve fibers conduct a lot slower than your motor reflex to drop that thing. So slow unmyelinated fibers function in processes such as secreting stomach acid or dilating the eyes pupil. Fast myelinated fibers function in processes such as those involving the skeletal muscles and sensory signals for vision and balance. Interesting disease with regards to the myelin sheath. Tay-Sachs disease, genetic disorder that is the lack of an enzyme that breaks down a glycolipid in the myelin sheath. As the glycolipid accumulates, there's a disruption of nerve conduction. So if you can't break down a glycolipid, anything that you can't break down in the body is going to just accumulate. So Tay-Sachs disease is an abnormal accumulation of a glycolipid in the myelin sheath. Well, what do you know about structure and function? If you change the structure of something or something starts taking an abnormal structure, it's going to change the function or disrupt the function. As this glycolipid accumulates in the myelin sheath, the myelin swells, causing a disruption in nerve conduction. The ultimate symptoms of this are blindness, loss of coordination, dementia, and death. I think it's usually within a year of diagnosis, or within a couple of years of diagnosis. Well, we know that neurons can't undergo mitosis, but axons sometimes are able to regenerate. So a damaged peripheral nerve fiber may regenerate if the soma is intact and the neural lemma remains. Keep that in mind. If the soma is intact and some neural lemma remains. What's the neural lemma, guys? What's the neural lemma we just went over a minute ago? So the neural lemma is the outer layer of the Schwann cell myelination. So the damaged peripheral nerve fiber can regenerate if the soma is intact and some neural lemma remains. So at the time that an axon is severed, the fiber, the axon distal to the cut, will not survive due to its inability to synthesize proteins. So the Schwann cells degenerate and macrophages move in and clean up the tissue debris. the muscle cells that are deprived of their nerve supply will undergo denervation atrophy. Because the target cells of a neuron are going to stimulate some growth factors and secrete some growth factors back to the soma of the neuron. The soma will lose some of the effects of those growth factors, and the soma can swell. The endothelium reticulum can break up and the nucleus moves off center. At this point, many neurons will die. Nevertheless, if it does not die, the axon stump will start to sprout growth processes. Axon stump will start to grow, to sprout growth processes. And near the cut, the Schwann cells and the basal lamina and the neural lemma will form a regeneration tube. Schwann cells produce cell adhesion molecules, CAMs, and nerve growth factors that enable a neuron to regrow to its original position, original destination. When one of the nerve growth processes from the axon stump enters the regeneration tube, it grows rapidly while all the other growth processes retract. The regeneration tube will guide the growing sprout back to their original target, and the synaptic contact is reestablished. When synaptic contact is reestablished, the soma can shrink back to its normal size and appearance, and the reinnervated fibers will regrow. Questions about the steps? Any questions so far? Schwann cells and endoneurium. Remember, endoneurium is the connective tissue that surrounds that neural lemma on the myelin. Are required for nerve fiber regeneration. Since the central nerve fibers lack these, the central nerve fibers cannot regenerate. So because they don't have an endoneurium, they don't have Schwann cells, they cannot regenerate. However, because the central nervous system is mainly encased in bone, it tends to suffer less trauma than the peripheral nervous systems do. Any questions? So electrophysiology, key questions. How does a neuron generate an electrical signal? And once it generates an electrical signal, how does it transmit a meaningful message to the next cell? Do you remember when we talked about cells, we talked about electrical potentials? So electrical potentials or voltage is the same as any battery in your house. There's an electrical difference in the concentration of charged particles between one point and another. It's a potential energy source that can produce an electrical current. So my typical battery in my house, or not my typical one, but an example of a battery in my house is a 9-volt battery that we put in the fire alarm and in the carbon monoxide detector. And this when we say 9-volt battery, that's because that's the membrane potential of the battery, 9 volts. One side of the battery has a more positive charge. One side has a more negative charge. Well, what do I do with this battery? It's not very helpful if it just stays in the packaging. What do we do with it? Why do we even keep them around? Go ahead, Becky.
You put them, like you said, in the smoke detector. So you would take it out and plug it in or clip it in.
How do you click it in?
You put the, I don't know if it's you put the negative with the positive.
Okay. Put a negative with a positive.
It has like little sensors, like metal.
Do me a favor. Let me say something. Have you ever licked the battery?
No.
Okay, Becky, you need to live a little. Anyone else ever licked a battery? When you were really little, you've licked the battery.
Oh my God, don't judge me, but it's kind of like a stingy filling. No, really, I have the one time. I was littler. I think I was doing something like me and my mom were changing like my batteries out to my toys and stuff. And I did the one time and it kind of was like a little bit of like a shocky feeling.
See, you don't ever forget that feeling.
No.
Yeah, that's why Becky needs to try it, because obviously she hasn't had the full life experience.
I think I'm good.
So, why did it shock you, Jade?
That I kind of really I don't know if it's because of like the voltage connecting to, I don't know, because it's kind of like your tongue's obviously like wet from saliva. So I don't know.
Your saliva has ions in it and you
Yes.
generate a current.
Yeah, so it like, I guess, connects to charge, right?
Yeah, it's your saliva allows a current to be generated.
Okay.
And so the whole reason a battery works is because we have a separation in charge. And so this will flow once we plug it in, or we decide we're going to lick it just to see what happens. Once we plug it in, the charge starts moving over to the other side. A dead battery is when there's no longer any driving force for the charge to keep moving, because they're equal on both sides. This is the same as a membrane. We have this membrane potential because we have this separation in charge. If we allow that charge to flow, we generate a current, and that current we can couple to other things to do work, right? We talked about a reaction coupling. That's the whole point. we don't have to worry about having a battery, our membrane potentials going dead because they're constantly being recharged. Some of us have really fancy rechargeable batteries. I think that's the battery in my car because I have a hybrid. We don't have to worry about our batteries going dead because they're constantly being recharged. Our membranes work the same way. They're constantly being reset. There's constantly a separation and charge being reset. That's the same thing as a membrane potential. If you think membrane potential is a potential energy source because of a separation of charge that's being maintained. So a current is a flow of charged particles from one point to another. The currents are created by the flow of sodium and potassium through gated channels, which can be opened and closed in response to different stimuli. The currents can be turned off and turned on. As long as the battery has a potential, which we call the voltage. So the voltage is the amount of charge that's separated. In your 9-volt battery, there's a potential separation of charge of 9 volts. I think in your most watch batteries, it's like 1.5 volts or something like that. So as long as there's a separation in charge, just like any polar molecule is, we can say that that membrane is polarized. In a resting neuron, the greater the number of positive ions are located outside of the battery, the cell, causing the membrane to be electrically charged or polarized. Because of the difference in charge. This charge difference is called the resting membrane potential. So it's the amount of potential energy you have within that separation of charge. Guys, this is a really important concept because it's really, we're gonna see it over and over again until the end of this semester. Potentials result from the diffusion of ions down their concentration gradients and the selective permeability of the membrane to some ions and the electrical attraction of cations and anions to one another. So the opposite charges across the membrane are attracted to one another. But the membrane is only selectively permeable to allow certain things through. However, with channels in the membrane, some ions can diffuse through. In neurons, the typical resting membrane potential is about minus 70 millivolts, with there being a lot more negative charges, negative 60 millivolts, more negative charges in the inside of the cell versus the outside of the cell. So the inside of the cell is about 70 millivolts more negative than the outside. Potassium has a much higher concentration inside the cell. Sodium has a much higher concentration outside of the cell. And a lot of negatively charged proteins are confined within the cell. With this in mind, the factors that are determine and maintain the resting membrane potential. The key one is potassium ions. They have the greatest influence on the resting membrane potential because the membrane is most permeable to potassium than any other ion. Potassium diffuses freely through the ion channels, leaving larger negatively charged anions behind in the cytoplasm. However, some potassium is attracted back by the anions in the cytosol that are stuck there, the negatively charged proteins that are stuck there. Also, another factor that's important in determining the resting membrane potential is sodium ions are about 12 times more concentrated in the extracellular fluid than in the intracellular fluid. We have some slow leaks back into the cell of sodium, but overall it's about 12 times. Why is it that much more concentrated? Because we have the sodium potassium pump. You remember that that's constantly pumping sodium against its concentration gradient and constantly pumping potassium into the cell against its concentration gradient. This membrane potential, this uneven distribution, only pertains to a very thin film along the plasma membrane and is not found throughout the rest of the cell. Remember, they're constantly attracted to one another too. So the negatively charges inside are attracted to the positively charges on the outside. What if the plasma membrane of a neuron had more sodium leak channels than potassium leak channels? What effect would this have on the resting membrane potential? It would destroy it. If we let sodium just keep leaking into the cell, there will be no separation charge at that point. They'll be equal on both sides. So there's three basic kinds of gated channels. There's channels that are involved in opening and closing in response to a stimulus. There's mechanically gated channels that are involved in opening in response to a pressure. Sorry, let me back up. Chemical stimulus is usually a ligand. Ligand binds to the channel. Mechanical stimulus is almost always a pressure. Membrane potential, voltage gated channels are a change in voltage that opens or closes the channel. These different kinds of gated channels give nerve and muscle cell membranes the property of excitability. So ligand-gated channels are going to open in response to specific chemicals. Chemical ligands include neurotransmitters, hormones, and ions. They're mainly concentrated at the synapse. There's numerous ones in the dendrites and the cell bodies of interneurons and motor neurons. Mechanically gated channels are going to open in response to pressure or vibration. We find these in hearing receptors, stretch receptors, and touch receptors. You push it, you bump it, and it opens. Here, you bind a chemical to the channel and it opens or closes. Voltage gated channels are going to participate in the generation and conduction of action potentials or electrical firing, because they're going to open and close in response to changes in voltage or membrane potential. AKA, remember, membrane potential and voltage are the same thing. These are mainly located along the neuronal axon. There's two basic types of electrical signals. There's graded potentials and action potentials. Graded potentials work short distance only. Action potentials are communication over long distances. Which potential travels the greatest distance? As you touch a pen, a graded potential develops in the sensory receptor in the skin of the fingertips. Once the inner neurons in the cerebral cortex are activated, perception occurs. And you can feel the surface of the pen. You can assess what it feels like. Is it smooth? Is it rough? Graded local potentials are changes in the resting membrane potential of the neuron that are occurring at or nearby the part of the cell that's stimulated. So graded potentials vary in magnitude according to the strength of the stimulus. They're decremental and can undergo summation. So they get weaker as they spread away from where the point of where they started, the point of origin. And they also can add together or cancel one another out. They're reversible. Once the stimulus ceases, the cation diffusion returns the voltage back to the resting membrane potential. They're inhibitory or excitatory, meaning that they can hyperpolarize or depolarize the membrane. What does it mean to hyperpolarize? It means to make the membrane potential more negative than it was before. Depolarization means to make it more positive than it is normally, making there less separation in charge than there was before. Remember, polarity is a separation in charge. So if we depolarize something, we're going to make it so there's less separation in charge. If we hyperpolarize it, we're going to make it a bigger separation in charge than it was before. Keep that in mind. So graded local potentials means that the membrane potential can vary in amplitude. The greater the stimulus strength, the larger the amplitude of the graded potential. A more intense and prolonged stimulus is going to result in more gated ion channels being open for a longer time. The result is that more sodium is going to enter the cell, and voltage changes are going to be more than it would be with a weaker stimuli. This relationship between the stimulus strength and the amplitude also exists in a hyperpolarizing membrane potential. Remember, that's what's going to make it more negative. Depolarizing is going to make it more positive. Hyperpolarizing meaning it's going to make it more negative. If sodium enters the cell, it's going to make the inside of the cell more positive. In a hyperpolarizing, it's going to make that inside of the cell more negative than it was. So a larger stimulus opens more ligand-gated channels and more ions are going to flow across the membrane. Because graded potentials are of varying amplitudes, they're also able to add together or summate or to cancel each other out. The net result is that we can have a smaller or larger summated graded potential. Nevertheless, because they die out, meaning they're decremental, graded potentials are only useful for short distances. Questions so far? Hyperpolarizing and a depolarizing graded potential. Depolarizing graded potentials, a stimulus that causes a reduction of the difference in the charge across the membrane. So it makes the inside of the cell less negatively charged with respect to the outside of the cell, the extracellular fluid. If it depolarizes, it's going to make it less, there's going to be a smaller separation charge, making the inside of the cell less negative. Hyperpolarizing, meaning that the stimulus causes the cell to become more negatively charged, hyperpolarizing. Rather than have it be negative 70 millivolts, it's going to be a negative 75 or negative 72. Depolarizing, meaning rather than having the membrane potential be negative 70, it's now negative 65. There's a balance between these two types of potentials. This is very important in allowing a neuron to process many inputs of incoming information. Some examples: acetylcholine, one of the probably the most famous neurotransmitter, the one we know most about, usually causes depolarization, with sodium entering the cell, making the cell's membrane more positive. So it's likely to reach a threshold potential and fire an action potential, which we'll talk about next. Glycine causes hyperpolarization, causing the cell membrane to become even more negative. So it's less likely to reach a threshold and fire an action potential. Whether the membrane potential becomes more negative or more positive depends on what type of channel opens. And these potentials can occur either as the opening of mechanical or ligand-gated channels. And this is not really a good location for this question. I should have thought more about where it's located. Which type of potential does not decay with distance? The action potential is the one that's not going to decay with distance. Remember, the graded potentials are decremental. So they decay. The further away they are from where they started, they diminish out. Guys, I know it's a little early for a break, but let's take 10 minutes and come back and work on action potentials.
Sounds good, thanks.
Okay.
As my dog, my teaching assistant is here snoring in my lap. You know you're not helping things this morning, right? Just a sec.
You've got cake too.
I know, and we're not very late. That's why we would normally wait another 15 minutes, but this is. Not really before they could even see you. Almost on that now. I'll let you know. I think this one and I'll let you know. Hi. Determined to learn to use the Instant Pot, Mary. Okay. I saw a much bigger one at Walmart. Let's learn to use this one first. Let's do that. Let's do that. I'm not firing on all cylinders this morning. Kate or Kat Roberto, are you here?
Yes, I'm here.
What was your question in your email?
Oh, okay.
There was
So
something about the practice.
yes, so one of the questions, and I kept thinking this might have happened to some of the other ones, but I really caught it on, I think it was the last question I had.
Do you
Um,
remember what it was like, what it looked like?
Yes, let me go back to, because I took a screenshot of it and emailed it to you.
I
So
know
it
you
said-
did, and I got busy doing other stuff last night. That's
Oh,
why.
yeah, that's okay. So it said, identify the correct statements regarding the treatment of fractures. And you can check all that apply. So it was the correct,
Give me one
treatment.
second here. I'm going to go into it. Mm. Hopefully. Okay. Well, and it was, okay, so identify all of the correct processes. Give me one second here.
Mhm.
Wasn't that one? Okay, it's this one.
Yes,
Okay.
that's it. So I selected, let's see, open reduction involves the surgical exposure of the bone and use of plate screw. So that one, so third, fourth, and the fifth, yeah, third, fourth, and fifth one. So that fifth one is obviously I got that wrong, and I see why, because it said, oh wait, no, I'm sorry, these are out of, wait, is this out of order? Oh no, I'm sorry. So it says I got that wrong because it says amplifying the effects, and it was supposed to be I forget what it's called, but I understood why I got that one
Suppressing
wrong.
effects. Okay, suppressing the effects.
Yeah,
All right.
right.
What was the other
And
one?
then, so the thing that it told me though was that I was supposed to select all four, and I got points deducted because I only selected these two. But most fractures, it says, are set by open reduction, which is wrong. Most fractures are set by the closed reduction. And then it also told me that I was supposed to select traction is used to treat fractures of the
Wait,
femur in adults,
Okay, so
but
most
that's for children. Mostly is used for children. And so then it took more points away. And I was like,
well, how many points did you lose? Can I ask?
probably, let's see, probably wasn't that much. So it just gave me a 0.16 out of like 0.32.
I'm gonna
But
do
it
something.
did that on like some other questions too, but this was the one that I really like caught it. And I
Okay,
was like, I don't think this is right.
let me look at your grade.
Unless I'm misunderstanding how it's like grading thing sometimes.
It's okay. I already updated your grade, so I don't know what it was before. Let me. We may need to revisit this again after class.
Yeah, that's fine.
Yeah,
Yeah,
I'm
that's
sorry.
okay. We
Well,
can do
I
that.
wondered if it was something that I could easily look at right now while we were here, but I don't think I can easily do it.
Yeah, that's okay. That'll be better because I have some other questions for you
Okay.
then anyway, so
Okay.
that's fine.
Okay,
Thank you.
you're welcome. No. Okay. Wrong one. See, what was that? We heard that. Huh?
It's my classmate. She's just getting out of control.
Okay. Okay. So action potentials are dramatic changes produced by voltage gated ion channels. So they occur where there is enough of a density of voltage gated channels. This is key. Because most of the cell soma, remember that's the cell body, most of the cell soma only has about 75 channels per micrometer squared. However, the trigger zone has 350 to 500 channels per micrometer squared. So if a strong enough excitatory local potential arrives at the trigger zone, it can open these channels and generate an action potential that will move down the axon. An action potential is going to be a rapid up and down shift in the membrane's potential. So the way that an action potential works is we have these gradual, here we're at minus 70 millivolts. Remember, that's our resting membrane potential. We can have small depolarizing local potentials, and we can have hyperpolarizing local potentials, which are going to result in the membrane becoming more negative. If there are enough of them that they sum to produce, and so that we have enough that they're and positive ones, that they're not canceling one another out, but they're actually adding to each other, causing the membrane potential to become less and less negative. So it becomes closer to being more positive, becomes less and less negative. At a certain potential of minus 55 millivolts, this is a threshold level. we will initiate an action potential, but we have to reach this minus 55. We have to have enough depolarizing membrane potentials that aren't being canceled out by hyperpolarizing membrane potentials that we can reach this minus 55. So when a steadily rising local potential arrives as a local current at the axon hillock, remember that's this little area right here, it's an axon hillock, it will depolarize the membrane. If this membrane arises to the critical depolarization voltage, the threshold of negative 55 millivolts, it's going to open voltage gated channels. So we remember how we have 3 different types of gated channels. We have voltage gated channels, we have mechanically gated channels, and we have chemically gated channels. These are voltage gated channels. So local potential rises to the critical depolarization threshold. It will open voltage gated channels. At this point, we initiate an action potential because the voltage gated sodium channels are going to open quickly. Going to happen just like that. The potassium channels are going to open also, but they're going to have to open a lot slower. A few sodium channels will open. But as the sodium enters the cell, it's going to further depolarize more of the membrane, causing more channels to open. So this is a positive feedback loop where we reach threshold, the sodium channels are going to quickly open, potassium channels are going to start to open. As the sodium channels are opening very quickly, it's going to cause more depolarization and more of the channels to reach this threshold, causing more sodium channels to open, resulting in this positive feedback loop where the membrane voltage is going to rise very quickly in this depolarization. Remember what depolarization means. It means that it's going to become more it's going to be more positive. There's going to be less separation in charge. And ultimately, it's actually going to reverse, and the inside of the cell is going to be more positive than the outside. So as the potential rises past 0 millivolts and peaks at positive 35 millivolts, the sodium channels at this point get inactivated. Remember, these are all channels that are opening via changes in voltage. So the sodium channels are going to get inactivated and begin closing. At this point, remember we had potassium channels that were slowly opening initially. Well, they're now fully open. And potassium moves out into the extracellular fluid, which is going to polarize the membrane, repolarize the membrane. Because as it moves out, the inside of the cell is going to become more negative. So the voltage becomes more negative. The action potential has this rapid up and down motion as the voltage reaches threshold and the voltage returns to the resting membrane potential. The potassium channels, they're slower to open and they're slower to close. So the potassium channels are going to stay open longer than the sodium channels, more sodium is going to leave the cell than, more potassium is going to leave the cell than sodium. And the membrane potential is going to become 1 to 2 millivolts more negative than the original resting membrane potential, so it's going to become like negative 71 or negative 72 millivolts. So this is going to result in a hyperpolarization of the membrane. During the action potential, the sodium and the potassium are switching places across the membrane because they're diffusing. During the hyperpolarization, because the sodium is gradually diffusing into the cell, the membrane voltage is gradually going to return to the resting membrane potential. Right here. I know that was fairly quick and there were a lot of steps. I'm going to go through it again. I'm going to go through it a little faster, but I want you to understand the sequence here. So a steadily rising depolarizing potential is summating if it reaches the axon hillock and it has a critical depolarization voltage of minus 55 millivolts, it's going to open sodium and potassium channels. The sodium channels are going to open quite quickly. The potassium channels are going to be a lot slower to open. A few sodium channels will open, but as they open, they're going to cause more of the membrane to reach the threshold potential of minus 55 millivolts, causing more sodium channels to open. So this is a positive feedback loop where some sodium channels open, they change the voltage becomes more easily reached to threshold. And so it's a quick swing of a depolarization. As the potential peaks at about plus 35 millivolts, so it's been reversed, the polarity, the sodium channels are inactivated at this voltage and they start to close. At this point, the sodium channels are closing, but the potassium channels are fully open. So potassium starts leaving the cell, causing the inside of the cell to become more negative again. Potassium channels are slower to open and they're slower to close. And so even though all the sodium channels are now closed, the potassium channels are open for a little longer. This results in a hyperpolarization of the membrane, where the membrane is even more negative than the resting membrane potential. Sodium will start leaking into the cell, bringing allowing for recovery from the hyperpolarization to the resting membrane potential. Questions? So at the resting membrane potential, both the sodium and potassium channels are closed. When threshold is reached, the sodium channels are going to quickly open. The potassium channels are going to begin to open, causing depolarization of the cell. When depolarization ends, because we reach that positive 35 millivolts, which is going to be the voltage at which the sodium channels are going to close. The potassium channels are now completely open and they repolarize the cell. So what is threshold? What is the status of the sodium and potassium gates at that point? At threshold, the sodium and potassium gates are the sodium gates before threshold, they're both closed. At the threshold, they'll both start to open, but the sodium gates are going to open a lot quicker. Depolarization, the sodium channels are opening fast. And as some open, it's going to cause the depolarization to occur faster, causing more sodium channels to open. And the potassium channels are still slowly opening. During repolarization, at that peak of positive 35 millivolts, the sodium channels are going to close. And the potassium channels are going to be fully open. Because the potassium channels are slower to open, they are slower to close. So the hyperpolarization is that the sodium channels are still closed, but the potassium channels are slowly closing. So what I want you to do tonight to understand this, what's going to occur next, is figure out what the status, write down what the status is of these gates. Make sure you understand this process. Because we're going to build on it now, but if you don't understand this, it's going to make the next part harder to understand. So action potentials, all or none law. So either they occur and threshold is reached, the action potential is fired, and it has a maximum of positive 35 millivolts. However, if the threshold is not reached, no action potential will ever be generated. If a stronger stimulus occurs that results in a depolarization above threshold, it doesn't matter because all action potentials are the same strength. So it's an all or nothing. Either it happens completely or it doesn't happen at all. And all action potentials are going to have the same amplitude every time, regardless of the strength of the original potential that results in reaching threshold. Action potentials are also non-decremental. They don't get weaker with distance. They keep being reinitiated. An action potential at the end of the axon is not weaker than one at the next to the trigger zone. They're also reversible. If the neuron's membrane reaches threshold, the action potential always goes to completion. I'm going to skip something for 1 second. I'm going to come back to it. So local potentials are produced by gated channels on the dendrites and soma. These are ligand gated channels. Action potentials are produced by voltage gated channels on the trigger zone and axon. Local potentials may be positive or negative voltage changes. Action potentials begin with depolarization. A graded potential is a potential that's proportional to the stimulus strength. An action potential is all or nothing. Either it doesn't occur at all or it exhibits the same peak voltage regardless of the stimulus strength. Local potentials are reversible. They return to the resting membrane potential if the stimulus ceases. Action potentials are irreversible. Once they start, they go to completion. Local potentials, they have effects for they only are effective for short distances from the point of origin. Action potentials are self-propagating. They have the greatest effect from the point of origin. They're self-propagating. The stimulus had the action potentials has the same amplitude at the axon helix that it has at the end of the axon. And it's self-propagating, so it continues itself. Local potentials are decremental, meaning they get weaker with distance. And action potentials are non-decremental, meaning they have the same strength the whole way. With this in mind, one thing that action potentials, remember, they're all or nothing, they're self-propagating. And they only move in one direction. They're self-propagating, but they only move in one direction because we have refractory periods. During an action potential and a few milliseconds afterwards, it's very difficult or impossible to stimulate the region of a neuron to initiate another action potential right there. Because we have an absolute refractory period and a relative refractory period. During the absolute refractory period, the sodium gates are open. And until they're fully closed, you can't initiate another action potential. So no stimulus during the absolute refractory period, right here until right here when the sodium gates are completely closed. You cannot initiate another action potential. So this is the absolute refractory period. Unless they're fully closed, they cannot be reopened. During the relative refractory period, a new action potential may be triggered, but only by an exceptionally strong stimulus. Because remember, this is the hyperpolarization time, where the membrane is even more negative than it would be normally. So it's a lot harder to reach threshold. So this relative refractory period is going to exist until the membrane is back to its resting membrane potential. So a new stimulus can open the sodium channels if we can reach threshold. So this is what keeps an action potential moving in one direction and not moving backwards. I mean, these are ions, they don't have a brain. They're only gonna move in one direction. They're gonna move in both directions. Well, what prevents them from moving backwards? This is what prevents them from moving backwards. So the maintenance of the resting membrane potential is possible due to what?
Deep.
Why do you say that?
Oh God. Um,
Because we're constantly making the separation in charge by the sodium and potassium pump that's moving things against their concentration gradient. And this pump requires ATP. That's why you're right. Does that make sense?
yeah, you just put it better than I would have.
So signal conduction along these unmyelinated versus myelinated fibers. In unmyelinated fibers, there's voltage gated channels across the entire axon length. In myelinated axons, the voltage ion channels are scarce in the myelin-coated regions. Remember, these are the area, myelin meaning the insulation. So in the areas that are covered with myelin along the axon, there's no voltage gated channels except at the nodes where there isn't myelin. So so there's fewer than 25 channels per micrometer squared in the internodal regions. And there's between 2,000 to 12,000 channels per micrometer at the gaps. So voltage gated along the whole entire unmyelinated axon, voltage gated channels. Myelinated axons, they're only specific. There's many channels at the nodes of Ranvier. Remember why we have myelin is it helps prevent leaks. But on top of that, we also have lots of channels at the regions where there is no myelin. This is important because the way that signals are conducted down unmyelinated nerve fiber is that the action potential occurs at the trigger zone. Sodium diffuses for a short distance along the plasma membrane. The resulting depolarization is going to open voltage channels immediately distal. Remember, this is that positive feedback loop. And the sodium and potassium channels open just as they did at the trigger zone, and a new action potential is initiated. It only moves in one direction because of the refractory periods. But there's a positive feedback loop where thing is going to peak at positive 35 millivolts. The potassium channels are fully open, and then it starts again, and it starts again, and it starts again, and it's continuous all the way down the axon. So steps 1 through 3 of this continuation is going to occur all the way until the end of the axon, because action potentials are self-propagating. So the result is that there's this non-interrupted wave of excitation along the fiber called continuous conduction. This is repeated along the entire length of the axon. And only the membrane ahead is going to be sensitive to being stimulated and being stimulated to produce an action potential because of the refractory periods. So this is this wave-like sequence where we don't lose amplitude from the beginning of the fiber to the end. Just keeps being initiated. The voltage gated channels are scarce in the myelin-coated internodal region. So, okay, I'm sorry, let me change topics here. Saltatory conduction is what occurs in the myelinated nerve fibers. So remember, in the unmyelinated areas, it's continually propagated all the way down the fiber. In the myelinated nerve fibers, it's a saltatory conduction rather than a continuous conduction. Because voltage gated channels are scarce in the myelin-coated nodal regions. There's no voltage channels where there's myelin coating the axon. Sodium is only going to enter the axon at the nodes of Ranvier. Remember how there's like 2,000 to 12,000 channels per micrometer squared in these gaps in the myelin. So each sodium has an electrical field around it. So sodium only enters at the nodes, and around each sodium ion, the sodium ions are going to repel each other because they're positively charged, and positive charges next to positive charges are repel each other, right? Only opposite charges attract. So no sodium moves very far in these regions, but the electrical repulsion of the individual ions is going to result in an energy transfer along the axon membrane. There's a lot of sodium entering, but it repels one another. And so they slowly, just based on their own electrical repulsion, move down. And they can't leak because there's not a lot of channels to leak out of. And it's also coated in myelin, which also makes it really hard to leak out of. So this is a gradual, they just gradually are moving down and there's no leakage. So they gradually are moving towards the next gap. Saltatory conduction is like a crowded subway car. I have ridden the subways occasionally when I was down in Washington, D.C., but I lived in Japan for a little while. And when I lived in Japan, I remember that there were people who were actually hired to push people into subway cars. Because they want to pack, they want to work to pack as many people as they can into the one subway car. Because nobody wants to have to wait for the next bus. So saltatory conduction is like a crowded subway car. The doors open, and this is where the sodium gates are going to open at a node. 20 people get on, and everyone has to push to the rear of the car to make more room. And they can only go in one direction. You can only go in one direction. No one passenger moves from the door to the rear, but the crowding and the transfer of energy from person to person forces those at the rear to move like sodium ions being pushed to the next node. And the events at one node are going to create excitation at the next node. So they're just gradually pushing one another down because there's so much sodium coming in and they can't go backwards, so they can only go forwards. And that initiates next action potential at the next node. Questions? As my mom's coughing out a lung in another room. Next, any questions? So myelin assists in two ways here. It seals up nerve fibers. It prevents leakage of sodium ions out of the axon. The higher concentration of sodium ions at the membrane allows for energy transfer to occur faster. The greater transfer of separation between the intracellular fluid and the extracellular fluid means that, actually, let me say this differently. So we know that the sodium and the potassium ions, the cations and the anions, the positively charged ions out here, the negatively charged ions inside are attracted to one another. They can hold each other in place for that reason. Because if you're attracted to someone, you can often hold them in wherever you are. Well, if there's myelin, that reduces that attraction just by physical distance here. And so things move a lot freer inside the cell and outside of the cell, because the attractive forces are weaker because of just the physical distance of the myelin wrapping. The width of this myelin wrapping around the axon. So the sodium ions move more freely within the axon, transferring energy from one ion to another. So saltatory conduction is going to move very fast at the internodal regions. But it's decremental. Conduction is slower at the nodes of Ranvier, but it's non-decremental. So it's slower at the nodes, but it's going to self-propagate. And it's not going to die out with distance. Questions? So conduction is going to occur fast in the expansive internodal regions, with excitation at one node of Ranvier creating excitation at the next node. Remember, it's a positive feedback loop. So the speed of conduction is determined by myelination, temperature, and diameter. If you're continually having to move a ball versus being able to pass the ball to someone else. So having one member dribble the ball or one person throw the ball. So continuous is having to dribble the ball. Saltatory conduction is being able to throw it and pass it. Or at that next node, the person may dribble it for a second and then they'll pass it again. Continuous is having to dribble it every time. So the input zone, just to overall nerve firing and conduction of an action potential, the input zone receives inputs from other neurons. Trigger zone is going to initiate an action potential. The conducting zone is going to conduct action potentials in an undiminishing fashion over long distances. The output zone is going to release neurotransmitter that influences other cells by synapsing with other cells. So input, trigger, initiate the action potential, self-propagation of the action potential, then releasing neurotransmitter that's going to influence whether action potentials are produced in the next set of cells. Any questions? So synapses, remember what a synapse is. What's a synapse? What's a synapse? Synapse is where one neuron is connecting with another cell. And in this case, a synaptic relationship between neurons. So one neuron's axon terminal is connecting with the cell body or dendrites of another neuron. I like to think of it as a snap on a shirt. One is connecting with the other. Signals arrive via the presynaptic neurons, which release neurotransmitter. So we have a presynaptic neuron. So this is the neuron before the synapse, which is going to release a neurotransmitter. And the next neuron, the postsynaptic neuron, is going to respond to that neurotransmitter. The presynaptic neuron can synapse with the dendrite, the soma or the axon of a postsynaptic neuron. Presynaptic neuron before the synapse releases a neurotransmitter. The postsynaptic neuron, that's the neuron after the synapse, is going to respond to the neurotransmitter. We have two different types of synapses. We have electrical synapses, where adjacent cells are joined by gap junctions. Guys, what are gap junctions? It's been a long time, but what are gap junctions? If you're not sure, Google it. What are gap junctions in cells?
The
Inter-
little, oh,
Go
the
ahead.
little connections between the two cells where stuff can flow in between, but it's
Right.
connecting them, holding them together.
Yeah, so it's a little channel that's made by each membrane has a half of the channel and they come together to make a full channel, right? Kate?
Yes. Yes.
Is it Kate or Tat?
Either one is fine.
Okay. They're found in, so the electrical synapses have gap junctions that allow for ions to diffuse directly from one cell into another. They're found in some neurons, some neuroglia, cardiac, and unitary smooth muscle. Chemical synapses are where neurons are going to communicate via neurotransmitters. Chemical synapses are the ones that are involved in memory and learning and can be the target for many prescription drugs and the site of action for why many drugs are addictive. So with electrical synapses, remember these, like Kat said, we're dealing, and Kat, I'm probably going to go back and forth between Kate and Kat, but I'll try really hard. Electrical synapses are where the action potential is going to spread from one neuron to the next neuron via gap junctions. There's no neurotransmitter necessary. They move extremely fast and they allow for two-way conduction. So they provide coordinated contractions of all the muscle fibers all at once. This is why all of your heart muscle contracts at one time and relaxes at one time, allowing for the heart to be an effective pump. A chemical synapse is where the axon terminal contains synaptic vesicles that have neurotransmitter within them. The synaptic cleft, this little gap in between the presynaptic neuron and the postsynaptic neuron, is this 20 to 40 nanometer gap. Remember what a nanometer is. So this is, nanometer is 10 to the minus negative ninth. very, very tiny gap between presynaptic and postsynaptic neurons. The presynaptic neuron has the vesicles. The postsynaptic neuron has receptors that bind the neurotransmitter. A spinal motor neuron is covered with this picture right here. This is a scanning electron microscope image showing that one motor neuron is covered with about 10,000 axon terminals from other neurons. 8,000 ending on its dendrites and 2,000 on the soma itself. In the cerebellum, one neuron can have as many as 100 synapses with other neurons. That's a lot if you think about it. That's a lot. The more synapses a given neuron has, the more abilities it has to incorporate information and process information. So neurotransmitters are molecules that are synthesized by neurons, released when a nerve signal reaches an axon terminal. And that neurotransmitter is going to have specific effects on the target cell's physiology based on what receptor it binds to on the postsynaptic neuron. Most neurotransmitters are released via exocytosis. What's exocytosis?
Is it where they break down the cells? I mean, get rid of the cells out of the, getting there.
What about get rid of the vesicles?
That's what I was trying to say.
So the vesicles are going to fuse with the membrane. Vesicles are going to fuse with the membrane and release their components into the synaptic cleft. Neurotransmitter is going to move across the synaptic cleft and bind to its receptor. Remember, neurotransmitters can have different effects based on whatever receptor they bind to. There are more than 100 neurotransmitters that have been identified, but most fall into four major categories: acetylcholine, amino acid neurotransmitters, which include glycine, glutamate aspartate, gamma amino butyric acid, or GABA, monoamines, which include the catecholamines, meaning epinephrine and norepinephrine and dopamine, serotonin and histamine, and purines, such as adenosine or adenosine triphosphate. Where have you heard of adenosine triphosphate?
It's used, it's the energy used.
So it's also a neurotransmitter. Some other categories of neurotransmitters, we have gases, nitric oxide and carbon monoxide. They're not synthesized and stored in synaptic vesicles. They diffuse out of an axon terminal and diffuse into the next postsynaptic neuron. Nitric oxide can also be a neuromodulator, which we'll talk about later. We have neuropeptides, cholecystokinin, and endorphins. Chains of about 2 to 40 amino acids stored in secretory vesicles rather than synaptic vesicles, and may also function as neuromodulators. More than anything, remember the different classes. Acetylcholine, you don't have to remember all of these. I mean, you're going to get familiar with some of the names, but know the major classes. No, acetylcholine is pretty famous. Know that one. No, we have amino acid neurotransmitters, monoamines, purines. We have gases and neuropeptides. We know what a neuropeptide is. So this is a tiny protein that's going to work as a neurotransmitter. Neurotransmitters can be excitatory, inhibitory, and sometimes their effect depends on what type of receptor is found on the postsynaptic neuron. So they're not always, no neurotransmitter is always excitatory or always inhibitory. Actually, let me not say that. Most neurotransmitters can be excitatory or inhibitory based on what receptor they bind to. The receptor is going to determine what happens next. So the receptor governs what effect the neurotransmitter will have on a target cell. Acetylcholine is the most common neurotransmitter, and it's excitatory at the neuromuscular junctions, but inhibitory at other synapses. There's multiple receptor types for each given neurotransmitter. For excitatory cholinergic, if you think acetylcholine, cholinergic, this is a receptor that's going to involve acetylcholine. Bear with me just for a second here. So all cholinergic receptors Becky, are you sick?
I feel like I am getting sick. Yes.
You sound like you're not well.
My kids say
Acetyl
that all the time. You're not well, Mom. You're just not well.
cholinergic receptors always bind to acetylcholine. Okay. So it mostly excitatory at the neuromuscular junctions, inhibitory at other junctions. So at excitatory cholinergic synapses, the neurotransmitter arrives at the terminal and it opens voltage gated calcium channels. If you remember, calcium is vital for nerve conduction. This is why. So the action potential, remember how it continues to, they're self-propagating. So they continue, they arrive at the axon terminal. When they arrive at the axon terminal, they're going to open voltage gated calcium channels. calcium is going to enter the terminal and trigger exocytosis of the synaptic vesicles. These vesicles are going to release their acetylcholine, and afterwards, empty vesicles are going to cycle back into the cytoplasm to be refilled by acetylcholine. So calcium is what's going to initiate the exocytosis of the vesicles containing the neurotransmitter acetylcholine. The vesicles are going to fuse with the membrane, release their acetylcholine, and then the vesicles cycle back into the cytoplasm to be refilled with more acetylcholine. The acetylcholine is going to diffuse across the synaptic cleft and bind to ligand-gated channels, they're called receptors. The sodium then, so it's going to open sodium-gated channels, and potassium is going to leave via the same gates. As sodium enters the postsynaptic cell, it's going to produce a local postsynaptic potential. If this postsynaptic potential, remember, as sodium enters the cell, it's depolarizing, so it's going to be an excitatory one. It's going to be a depolarizing local potential. If that potential is strong enough or persistent enough, it will open voltage-gated channels in the axon hillock and induce another action potential. During the events involved in the information transfer across a chemical synapse, which of the following steps would be directly interrupted by exposing a neuron to a calcium channel blocker? Guys, where does calcium act on this?
Nerve conduction.
Well, where on nerve conduction?
um, it says it enters the terminal and triggers exocytosis.
Yes. So where is it going to, what area would be interrupted by exposing a neuron to a calcium channel blocker?
A.
Yes. Drugs can modify the effects of neurotransmitters. Many drugs work on the effects of neurotransmitters. They can stimulate or inhibit the synthesis of a neurotransmitter. They can enhance or block the release of neurotransmitters. They can activate or block specific receptors that bind to neurotransmitters. They can stimulate or inhibit the removal of neurotransmitters from the synaptic cleft. One of the most addictive drugs in the world and possibly, in the US and possibly in the world is nicotine. Nicotine binds to cholinergic receptors and activates them. So rather than just having acetylcholine bind to its receptor, now we're introducing a drug that causes more activation of acetylcholine receptors because it mimics the structure of acetylcholine, resulting in the more release of dopamine. What is dopamine? Dopamine is a happy neurotransmitter. Allows people to feel calmer and happier. So it results in the release of more dopamine. That's why it's so addictive. So you get addicted to the effects of what the drug does. Questions? An inhibitory GABAergic receptor. Mom, what is that? Okay. Synapses that employ GABA aminobutyric acid or GABA work by the same mechanism as acetylcholine. However, the GABA receptor is a gated chloride channel. If you allow chloride to move into the cell, it's going to make the inside of the cell, because it's negatively charged, it's going to make the inside of the cell more negative, hyperpolarizing the membrane. Remember what happens if you hyperpolarize a membrane, you make it less likely to respond. So it's going to be an inhibitory response. So when chlorine enters a cell, the cell becomes more negative, resulting in the neuron being less likely to fire on action potential. Excitatory adrenergic synapses employ norepinephrine or adrenaline or other monoamines to act via second messenger systems. You remember what molecule was involved in second messenger systems? Often it's cyclic AMP. Adrenergic receptors are going to bind to things like adrenaline. So these are, rather than being opening a channel, ion channel, like ligand gated channel, these are going to work through generating a signal transduction pathway. So the neurotransmitter binds to a receptor and it starts a signal transduction pathway that involves a second messenger system like cyclic AMP. The receptor for The second messenger system is a G protein coupled protein. The receptor binds to the neurotransmitter. It activates a G protein, which then activates this enzyme called adenylate cyclase, which produces cyclic AMP, which goes on to have several effects. So that neurotransmitter receptor is coupled to a G protein. Binding of the neurotransmitter to the receptor results in the dissociation of a G protein that then binds to adenylate cyclase and converts ATP to cyclic AMP. The cyclic AMP then can go on to induce several different effects, such as production of an internal chemical that will open ligand-gated ion channels, allowing for the depolarization of the cell. The activation of cytoplasmic enzymes that can lead to a variety of metabolic changes and induce the transcription of genes, encoding enzymes resulting in metabolic changes. Even though excitatory adrenergic synapses tend to be slower than cholinergic or GABAergic synapses, cholinergic path synapses, adrenergic synapses work by signal amplification. So one neurotransmitter molecule can result in the formation of many cyclic AMPs that activate many enzyme molecules or induce the transcription to generate many mRNA molecules, resulting in the production of multiple enzymes. In synapses, there's always a synaptic delay. The time from the arrival of a signal at the axon terminal to the beginning of an action potential. So in all synapses, there's a synaptic delay. The neurotransmitter has to diffuse across the cleft. And then it has to start the activation. So all synapses have this delay. Well, how do we get rid of the neurotransmitter? We don't want it to keep occurring. We've got to be able to get rid of it. Sometimes we want something to happen and then we want it to stop. We can't let it just keep going or nothing else will happen. So we want to eliminate it by removing the neurotransmitter. So the neurotransmitter is going to, we can do it through three different ways. We can degrade the neurotransmitter. So there's an enzyme in the synaptic cleft that's going to break down the neurotransmitter. In the case of acetylcholine, it's acetylcholinesterase. Sorry. We can also reuptake the neurotransmitter, have it be reabsorbed by transport proteins back into the axon terminal. Monoamine oxidase is an enzyme that breaks up monoamine transmitters. Or we can have the neurotransmitter diffuse away into the extracellular fluid. So it happens through three different ways. Gets degraded, gets retaken up or it diffuses away. So we talked about the fact, we hinted to the fact that there's lots of drugs that work on neurotransmitters and their effects. One drug that lots of people are on because it's an antidepressant, anti-anxiety, is Prozac, also called fluoxetine. It inhibits the reuptake of serotonin. So it works on slowing down the elimination of serotonin. By slowing down how much it's being retaken up. If it stays in the synaptic cleft longer, it's going to be able to activate the next postsynaptic cells longer. Questions? Mom, what is that?
That's my phone
Okay,
telling me to do something.
okay. Neuromodulators. So moving on, neuromodulators are molecules secreted by neurons with long-term effects on entire groups of neurons, rather than just brief, quick effects of the neurotransmitters. So these have a longer effect than neurotransmitters, and they're going to affect a large group of neurons rather than individual neurons. They function in increasing the release of neurotransmitter by presynaptic neurons, adjusting the sensitivity of postsynaptic neurons to neurotransmitters, and altering the rates of reuptake and breakdown. So they're going to alter the effects that neurotransmitters have on other neurons. Some examples of neuromodulators. Nitric oxide diffuses into a postsynaptic cell and activates second messenger activities. Remember, this is cyclic AMP. So it relaxes smooth muscle to dilate small arteries and increase blood flow. This is the reason that, what is it? What's the thing that this works on? Viagra increases nitric oxide levels. Neuropeptides such as enkephalins, I think it's enkephalins, and endorphins inhibit spinal neurons from transmitting pain signals to the brain. This is why when I was out running one time and I'd accidentally cut my toe sometime while I was out running. And I was enjoying myself so much because my endorphins were so high that I got back and took off my shoe and realized that my shoe was just full of blood. And I hadn't felt it at all because I'd been having such a good time while I was out running anyway. So neuropeptides are really good in inhibiting pain signals. Other signals are hormones and neurotransmitters like dopamine and serotonin and histamine. One thing to keep in mind here, so hormones and neurotransmitters like dopamine and serotonin and histamine are also neuromodulators. So some neurotransmitters also act as neuromodulators. Some neurotransmitters act as hormones. Some neurotransmitters are hormones. Some hormones are neurotransmitters. What this means is that a neurotransmitter or hormone or a neuromodulator is not going to be defined by the chemical itself. It's because of the role that it plays in a given context. One chemical can play 2 or more roles depending on the situation. The more synapses a neuron has, the greater its information processing abilities. Remember, we saw that one synapse where that one synapse where one neuron in the cerebellum can have up to 100,000 synapses on it. So the more synapses a neuron has, the greater its information processing capabilities. A pyramidal cell in the cerebral cortex can have about 40,000 synaptic contacts with other neurons. Neural integration is the neuron's ability to process information, store and recall it, and make decisions. Then the decisions are based on the postsynaptic potentials initiated at the axon's trigger zone. Well, how does this happen? How do we get neural integration? We've you've seen some of this before, but we're going to spend the majority of the rest of the time talking about this neural integration. You ought to be up there. We have excitatory postsynaptic potentials, which these are depolarizing potentials. Bill, you can't be right there, buddy. We have inhibitory postsynaptic potentials. So depolarizing is excitatory. Remember, it's going to cause more sodium to flow into the cell, making the inside of the cell less negative. An inhibitory postsynaptic potential is a hyperpolarization triggered by a neurotransmitter that makes the inside of the cell more negative. Leo, sorry, disciplining my cat. The inhibitory is going to hyperpolarize the membrane. So more chlorine is going to be the result of either more chlorine flowing into the cell or potassium flowing out of the cell. So excitatory postsynaptic potentials makes a neuron more likely to initiate an action potential. Inhibitory postsynaptic potentials are going to make it much less likely to inhibit an action potential. Are these types of postsynaptic potentials, are they local or action potentials? Are they local potentials or action potentials? No, buddy, really, no. You guys, are they local potentials or action potentials? Let me ask this, are action potentials ever inhibitory?
No.
No, they're not. These are all going to be occurring on the dendrite or the soma or part of the axon, but they're never inhibitory. These are always excitatory. So these are the postsynaptic potentials that a neuron is going to receive lots of them. And ultimately, they're going to sum together or cancel one another out. And that will determine whether that neuron is going to fire an action potential. So excitatory postsynaptic potentials and inhibitory postsynaptic potentials are not going to dictate whether a neuron will fire an action potential, but it will determine the rate of firing by stimulating or inhibiting the production of more action potentials. So inhibitory postsynaptic potentials are going to create a hyperpolarization, allowing potassium to leave the cell is going to result in an inhibitory postsynaptic potential. Allowing chlorine to enter the cell is going to result in an inhibitory postsynaptic potential, hyperpolarizing the membrane. Allowing sodium to enter the cell is going to be an excitatory postsynaptic potential. And depolarize the membrane. So a single excitatory postsynaptic potential is not going to initiate a nerve impulse. Remember how they're decremental, they die out over distance. Because these are local potentials, they're weak, they don't self-propagate. So it's a process of adding multiple, summation is a process of adding multiple postsynaptic potentials and responding to their net effect. Yet multiple ones coming together to produce larger ones or canceling one another out. Leo, no, buddy. He's letting me know I've been sitting at the computer way too long. Temporal summation, temporal meaning time. So a temporal summation is when one presynaptic neuron is going to generate so many excitatory postsynaptic potentials that each potential is generated before the last one is faded. So it's happening, and before the last one is able to fade, the next one comes in. And so they're going to keep adding to one another. So all of them combined are going to end up with a voltage reaching threshold at the axon hillock. Spatial is where they're coming in from different areas on the dendrites on the soma. And because there's so many coming in at different areas on the dendrite or on the somas, they're going to add up just spatially. And result in an action potential being initiated at the axon hillock. Suppose the excitatory postsynaptic potentials are summating in response to simultaneous stimulation by neurotransmitters, glutamate, serotonin, and acetylcholine, released by 3 separate presynaptic neurons. Is this an example of spatial or temporal summation? Each one of these right here, we're looking at this one. This is temporal summation. Each one of these is a separate presynaptic neuron. One presynaptic neuron is sending multiple ones. That's temporal summation. When there's multiple ones that are all combining on one neuron and they're all sending signals, that's spatial. So suppose that excitatory postsynaptic potentials are responding in simultaneous stimulation by neurotransmitters, glutamate, serotonin, acetylcholine, released by 3 separate presynaptic neurons. Is this an example of spatial or temporal summation?
Spatial.
Is spatial. You guys, do you have any questions?
No.
Hey, I'm going to keep going for a few more minutes here. We will finish, we won't finish this today, but we will finish it next time. We will do the spinal cord and then we will start on the brain. The spinal cord is not that long. Which of the following is a true statement about neurons?
D.
So let's get traveling. I would say you're right.
I was a little lost reading that, but I figured it was just D because of the how it goes away from the cell body and axons.
Yeah, because we have those refractory periods. It can't go in either direction.
Okay.
Membrane depolarization is caused by what? Don't scroll back. Don't look too far back. Right here.
Into the cell.
So if the cell, if depolarization, meaning that the inside of the cell is becoming more positive. So this is a localized influx of sodium ions into the cell. Which of the following is not true about true synapses?
I could be wrong, but could it be C?
Say it again.
I said I could be wrong, but would it be C?
Yes. Because they can't bind to both sides, right?
Yeah.
Sodium potassium pumps help maintain the membrane potential by pumping sodium ions into the cell while pumping potassium ions out of the cell. No, I'm sorry, opposite. By pumping sodium out of the cell and pumping positively charged potassium ions into the cell. Guys, we will start on this 136, talk about presynaptic facilitation. We will finish this. We will do the spinal cord. You're gonna realize it's a much shorter chapter. And then we will start the brain.
Sounds good.
Okay. Have a good week.
Thank you. You as well.
Hey, Mary, I have a few questions
Yeah,
then for
give me
you.
1 second. I'm sorry. Give me 1 second. I just need to write down where we're at. 1 moment. I'm sorry.
No, that's fine. Take your time.
Learn my classes go a lot smoother if I remember where we left off with each PowerPoint. 1 second here. 136. Okay. All right. I'm going to stop sharing and I'm going to stop recording.